Ernest Rutherford came along in 1911 and gave us the gold foil experiment. And in the gold foil experiment, he took a foil of gold, like 3 atoms or so thick, and he bombarded it with a source of alpha particles, which it doesn't say here, but alpha particles, as we'll learn in the next chapter, are helium atoms that have a double positive charge. And so because they're positive, this is what makes this research kind of amazing. As they were to pass through what he thought was the atom in terms of the plum pudding model, since the atom was overall neutral, the alpha particles would pass right through the atom like that. He said this because it's neutral, the charges are evenly distributed, although the alpha particle is positively charged, all of the interactions in all 3 dimensions would cancel out. It might get repelled up, but it would be getting repelled down, or attracted up and down, left, right, forward, and back, all of those at the same time. So these alpha particles would just pass right on through the atom. But obviously this is not what happened. If you look at the picture here, Rutherford noticed that most of the alpha particles did pass through the gold foil, but a few of them actually deflected backwards in very large angles. And so he reasoned that the only way this could be possible, if this positively charged alpha particle were to come into contact with the atom, would it go backwards? It would only do that if it had a very, very densely located and massive nucleus that is positively charged itself. Opposites repel each other, so when the alpha particle comes towards the atom, if it comes near it, it'll get deflected on fairly large angles. If it hits it directly, it goes almost backwards and towards the source even occasionally. The neutron was discovered in 1932 by James Chadwick. It took much longer to discover because neutrons don't have a charge, so it doesn't interact with anything positive or anything negative chemically, or in any way that they were able to figure out at the time. But James Chadwick and others knew that the atoms must have something else in them because the masses of the protons and the masses of the electrons simply did not add up to the mass of the atoms. The reason that the mass of this neutron would be similar to the mass of a proton, and it was discovered that it is, and it also is not charged like they expected. It was discovered by taking more alpha particles again and bombarding them this time with beryllium. And when they did this in a particle accelerator, the result of it was a nuclear reaction in which the beryllium was transmuted into carbon, and it released a neutron. Now you can see, if you look closely here, the numbers of everything in this reaction. We have the number 9 here represents the mass number. That's the total number of protons plus neutrons. And if we add them up together, 9 and 4, you get 13. If we look at the right side of the equation, we have 12 plus 1 is 13. So the total number of protons and neutrons in this nuclear reaction has stayed the same. It follows the law of conservation of mass. Now if we look at the left side again, we've got that number 4 and that number 2. That together makes just the number of protons, and they add up to 6. That's the atomic number for these elements, which we'll get into later. We look at the right side, we have 6 and 0, which still adds up to 6. This picture here shows the scale of the atom and its nucleus and everything inside. So they take a chunk of lithium metal and you zoom into it and you see the individual atoms, which are spheres. And then zooming in even further to individual atoms, it says the atomic diameter is 10 to the negative 10th meters approximately, and that is equal to what chemists call 1 angstrom. And they just use that because you want the radius or the diameter of atoms to be simple whole numbers that make sense. So it's easier to say this atom is 1 or that atom is 2 and use angstroms instead of 10 to the negative 10th. Now if you look at the size of the nucleus encircled here, the nuclear diameter is 10 to the negative 15th meters. That's 1/100,000th the size of the entire atom. But it's almost the entire mass of the atom. 99.999% of it, roughly, is in 1/100,000th the size of the entire atom. And so to put this into perspective, if you have a marble as the nucleus, the outer surface of this marble atom, quote unquote, would be, I think, 3 football fields away. So, but it would contain all of the mass. So you can imagine when Rutherford was shooting these alpha particles at this gold foil, how unlikely it was for them to even strike the nucleus. But when they did, since you have such a densely packed nucleus of all the positive charge being right there, these positively charged alpha particles had an extreme repulsion to it. So they went backwards, or at least on very, very large angles. The table here shows you a comparison of the 3 subatomic particles. You can see the symbols given to them. You can see the relative charges. The proton has a +1 charge, the electron has a -1 charge, and the neutron is uncharged. They also have the masses and AMUs, but normally I like to consider them as relative masses, where the proton and the neutron are both 1, and the electron is essentially 0. It also has the location of the atom. The protons and neutrons are located in the nucleus, and the electrons are outside the nucleus. So atomic mass units, or AMUs, are the standard unit of measure of the relative masses of individual atoms. Keep in mind it does say relative, and that's important because it means it's not the actual masses. It's just how are these values in relation to each other. And so 1 AMU is defined to be exactly equal to 1/12 the mass of a carbon-12 atom, which was probably just chosen because of the importance and prevalence of carbon, and other than that, it's just arbitrary. They could have chosen nitrogen or hydrogen, but it's not.